Chapter 3 Metals and Nonmetals. In class 9, you have learned about various elements. You have seen the elements can be classified as metals or nonmetals on the basis of their properties. Think of some uses of metals and nonmetals in your daily life. What properties did you think of while categorize elements as metals or nonmetals? How are these peoples related to the use of these elements? Let us look at some of these properties in detail. Physical properties. Metals. The easiest way to start grouping substances is by comparing their physical properties. Let us study this with the help of the following activities. For performing activities 3.1 to 3.6, collect the samples of following metals: iron, copper, aluminium, magnesium, sodium, lead, zinc, and other metal that is easily available. Activity: take samples of iron, copper, aluminium, and magnesium. Note the appearance of each sample. Clean the surface of each sample by rubbing them with sandpaper and note their appearance again. Metals in their pure state have a shining surface. This property is called metallic luster. Activity: take small pieces of iron, copper, aluminium, and magnesium. Try to cut these metals with a sharp knife and note your observation. Hold a piece of sodium metal with a pair of tongs. Caution: always handle sodium metal with care. Dry it by pressing between the folds of a filter paper. Put it on a watch glass and try to cut it with a knife. What do you observe? Comment this. You will find that metals are generally hard. The hardness varies from metal to metal. Activity: take pieces of iron, zinc, lead, and copper, places any one metal on a block of iron and strike it 4 or 5 times with a hammer. What do you observe? Repeat with other metals. Record the change in the shape of these metals. You will find that some metals can be beaten into thin sheets. This property is called malleability. Did you know that gold and silver are the most malleable metals? Comment this. Activity: list the metals whose wires you have seen in daily life. The ability of metals to be drawn into thin wires is called ductility. Gold is the most ductile metal. You will be surprised to know that a wire of about 2 km length can be drawn from 1 gram of gold. It is because of their malleability and ductility that metals can be given different shapes according to our needs. Can you name some metals that are used for making cooking vessels? Do you know why these metals are used for making vessels? Let us do the following activity to find out the answer. Activity: take an aluminium or copper wire. Clamps this wire on a stand as shown in figure. Fix a pin to the free end of the wire using wax. Hit the wire with a spirit lamp, candle, or a burner near the place where it is clamped. What do you observe? After some time, note your observations. Does the metal wire melt? A stand, clamp, metal wire, free end of wire, pin, wax, burner. Figure: metals are good conductors of heat. The above activity shows that metals are good conductors of heat and have high melting points. The best conductors of heat are silver and copper. Lead and mercury are comparatively poor conductors of heat. Do metals also conduct electricity? Let us find out. Activity: set up an electric circuit as shown in figure. Place the metal to be tested in the circuit between Terminals A and B are as shown. Does the bulb glow? What does this indicate? Figure. Metals are good conductors of electricity. Battery, bulb, clips, switch. Insert sample to be tested. AB. You must have seen that the wires that carry current in your homes have a coating of polyvinyl chloride (PVC) or a rubber-like material. Why are electric wires coated with such substances? What happens when metals strike a hard surface? Do they produce a sound? The metals that produce a sound on striking a hard surface are said to be sonorous. Can you know? Say why school bells are made of metals? Comment this. Non-metals. In the previous class you have learned that there are very few non-metals as compared to metals. Some of the examples of non-metals are carbon, sulfur, iodine, oxygen, hydrogen, etc. The non-metals are either solids or gases except bromine, which is a liquid. Do non-metals also have physical properties similar to that of metals? Let us find out. Activity. Collect samples of carbon, coal or graphite, sulfur and iodine. Carry out the activities to and with these non-metals and record your observation. Compile your observations regarding metals and non-metals in table. Table. Element, symbol, type of surface, hardness, malleability, ductility, conduct, electricity, sonority. Comment this. On the basis of the observation recorded in table, discuss the general physical properties of metals and non-metals in the class. You must have concluded that we cannot group elements according to their physical properties alone, as there are many exceptions. For example, 1. All metals except mercury exist as solid at room temperature. In activity, you have observed that metals have high melting points, but gallium and cesium have very low melting points. These two metals will melt if you keep them on your palm. 2. Iodine is a non-metal, but it is lustrous. 3. Carbon is a non-metal that can exist in different forms. Each form is called an allotropy. Diamond, an allotropy of carbon, is the hardest natural substance known and has a very high melting and boiling point. Graphite, another allotropy of carbon, is a conductor of electricity. 4. Alkali metals, lithium, sodium, potassium are so soft that they can be cut with a knife. They have low densities and low melting points. Elements can be more clearly classified as metals and non-metals on the basis of their chemical properties. Activity. Take a magnesium ribbon and some sulfur powder. Burn the magnesium ribbon. Collect the ashes formed and dissolve them in water. Test the resultant solution with both red and blue litmus paper. Is the product formed on burning magnesium acidic or basic? Now, burn sulfur powder. Place a test tube over the burning sulfur to collect the fumes produced. Add some water to above test tube and shake. Test the solution with blue and red litmus paper. Is the product formed on burning sulfur acidic or basic? Can you write equations for these reactions? Comment this. Most non-metals produce acidic oxides when dissolved in water. On the other hand, most metals give rise to basic oxides. You will be learning more about these metals oxides in the next section. Questions. Do this and comment this. Chemical properties of metals. We will learn about the chemical properties of metals in the following section. For this, collect the samples of following metals: aluminium, copper, iron, lead, magnesium, zinc, and sodium. What happens when metals are burnt in air? You have seen in activity that magnesium burns in air with a dazzling white flame. Do all metals react in the same manner? Let us check by performing the following activity. Activity caution. The following activity needs the teacher's assistant. It would be better if students wear eye protection. Hold any of the samples taken above with a pair of tongs and try burning over a flame. Repeat with the other metal samples. Collect the product if formed. Let the products and the metal surface cool down. Which metals burn easily? What flame's color did you observe when the metal burnt? How does the metal surface appear after burning? Arrange the metals in the decreasing order of their reactivity towards oxygen. Are the products soluble in water? Comment this. Almost all metals combine with oxygen to form metal oxides. Metal plus oxygen tends to metal oxides. For example, when copper is heated in air, it combines with oxygen to form copper 2 oxide, a black oxide. 2Cu plus O2 copper tends to 2CuO, copper 2 oxide. Similarly, aluminium forms aluminium oxide. 4Al aluminium plus 3O2 tends to 2Al2O3 aluminium oxide. Recall from chapter 2 how copper oxide reacts with hydrochloric acid. We have learned that metal oxides are basic in nature, but some metal oxides such as aluminium oxide, zinc oxide show both acidic as well as basic behavior. Such metal oxides which react with both acids as well as bases to produce salts and water are known as amphoteric oxides. Aluminium oxides reacts in the following manners with acids and bases. Al2O3 6HCl tends to 2AlCl3 plus 3H2O. Al2O3 plus 2NaOH tends to 2NaLO2 sodium aluminate plus H2O. Most metal oxides are insoluble in water, but some of these dissolve in water from alkali sodium oxide and potassium oxide dissolve in water to produce alkalis as follows. Na2O solid plus H2O liquid tends to 2NaOH aqueous. K2O solid plus H2O liquid tends to 2KOH aqueous. We have observed in activity that all metals do not react with oxygen at the same rate. Different metals show different reactivities towards oxygen. Metals such as potassium and sodium react so vigorously that they catch fire if kept in the open. Hence, to protect them and to prevent accidental fires, they are kept immersed in kerosene oil at ordinary temperature. The surface of metals such as magnesium, aluminium, zinc, lead, etc. are covered with a thin layer of oxides. The protective oxides layer prevents the metal from further oxidation. Iron does not burn on heating, but iron filings burn vigorously when sprinkled in the flame of the burner. Copper does not burn, but the hot metal is coated with a black colored layer of copper 2 oxides. Silver and gold do not react with oxygen even at high temperature. Do you know? Anodizing is the process of forming a thick oxide layer of aluminium. Aluminium develops a thin oxide layer when exposed to air. This aluminium oxide coat makes it resistant to further corrosion. The resistance can be improved further by making the oxide layer thicker. During anodizing, a clean aluminium particle is made the anode and is electrolyzed with dilute sulfuric acid. The oxygen gas evolved at the anode reacts with aluminium to make a thicker protective oxide layer. The oxide layer can be dyed easily to give aluminium particles an attractive finish. After performing activity, you must have observed that sodium is the most reactive of the samples of metals taken here. The reaction of magnesium is less vigorous, implying that it is not as reactive as sodium. But burning in oxygen does not help us to decide about the reactivity of zinc, iron, copper, or lead. Let us see some more reaction to arrive at a conclusion about the order of reactivity of these metals. What happens when metals react with water? Activity. Caution. This activity needs the teacher's assistance. Collect the samples of the same metals as in activity. Put small pieces of the samples separately in beaker half filled with cold water. Which metals reacted with cold water? Arrange them in the increasing order of their reactivity with cold water. Did any metal produce fire on water? Does any metal start floating after some time? Put the metals that did not react with cold water in breakers half filled with hot water. For the metals that did not react with hot water, arrange the apparatus as shown in figure and observe their reaction with steam. Which metals did not react even with steam? Arrange the metal in the decreasing order of reactivity with water. Figure action of steam on a metal, a glass wool soaked in water, metal sample, burner, stand, cork, delivery tube, hydrogen gas, water, stand. Metals react with water and produce a metal oxide and hydrogen gas. Metal oxides that are soluble in water dissolve in it to further form metal hydroxide. But all metals do not react with water. Metal plus water tends to metal oxide plus hydrogen. Metal oxide plus water tends to metal hydroxide. Metals like potassium and sodium react violently with cold water. In case of sodium and potassium, the reaction is so violent and exothermic that the evolved hydrogen immediately catches fire. 2K solid plus 2H2O liquid tends to 2KOH aqueous plus H2 gas plus heat energy. 2Na solid plus 2H2O liquid tends to 2NaOH aqueous plus H2 gas plus heat energy. The reaction of calcium with water is less violent. The heat evolved is not sufficient for the hydrogen to catch fire. Ca solid plus 2H2O liquid tends to CaOH whole 2 aqueous plus H2 gas. Calcium starts floating because the bubbles of hydrogen gas formed stick to the surface of the metal. Magnesium does not react with cold water. It reacts with hot water to form magnesium hydroxide and hydrogen. It also starts floating due to the bubbles of hydrogen gas sticking to its surface. Metals like aluminium, iron and zinc do not react either with cold or hot water, but they react with steam to form the metal oxide and hydrogen. 2Al solid plus 3H2O gas tends to Al2O3 solid plus 3H2 gas. 3FeS plus 4H2O gas tends to Fe3O4 solid plus 4H2 gas. Metals such as lead, copper, silver and gold do not react with water at all. What happens when metals react with acids? You have already learned that metals react with acids to give a salt and hydrogen gas. Metal plus dilute acid tends to salt plus hydrogen. But do all metals react in the same manner? Let us find out. Activity. Collect all the metal samples except sodium and potassium again. If the samples are tarnished, rub them clean with sandpaper. Caution. Do not take sodium and potassium as they react vigorously even with cold water. Put the samples separately in test tubes containing dilute hydrochloric acid. Suspend thermometers in the test tubes so that their bulbs are dipped in the acid. Observe the rate of formation of bubbles carefully. Which metals reacted vigorously with dilute hydrochloric acids? With which metal did you record the highest temperature? Arrange the metals in the decreasing order of reactivity with dilute acids. Write equations for the reactions of magnesium, aluminium, zinc and iron with dilute hydrochloric acid. Hydrogen gas is not evolved when a metal reacts with nitric acid. It is because HNO3 is a strong oxidizing agent. It oxidizes the H2 produced to water and itself gets reduced to any of the nitrogen oxides N2O, NO, NO2. But magnesium Mg and manganese Mn react with very dilute HNO3 to evolve H2 gas. You must have observed in activity 3.11 that the rate of formation of bubbles was the fastest in the case of magnesium. The reaction was also the most exothermic in this case. The reactivity decreases in the order magnesium less than aluminium less than zinc less than Fe. In the case of copper, no bubbles were seen and the temperature also remained unchanged. This shows that copper does not react with dilute HCl. Do you know? Aqua regia, Latin for royal water, is a freshly prepared mixture of concentrated hydrochloric acid and concentrated nitric acid in the ratio of 3:1. It can dissolve gold, even though neither of these acids can do so alone. Aqua regia is a highly corrosive fuming liquid. It is one of the few reagents that is able to dissolve gold and platinum. How do metals react with solutions of other metal salts? Activity. Take a clean wire of copper and an iron nail. Put the copper wire in a solution of iron sulfate and the iron nail in a solution of copper sulfate taken in test tubes. Figure. Record your observation after 20 minutes. In which test tube did you find that a reaction has occurred? On what basis can you say that a reaction has actually taken place? Can you correlate your observation for the activities and write a balanced chemical equation for the reaction that has taken place? Name the type of reaction. Reactive metals can displace less reactive metals from their compounds in solution or molten form. We have seen in the previous section that all metals are not equally reactive. We checked the reactivity of various metals with oxygen, water and acids. But all metals do not react with these reagents. So we are not able to put all the metal samples we had collected in decreasing order of their reactivity. Displacement reactions studied in chapter 1 give better evidence about the reactivity of metals. It is simple and easy. If metal A displaces metal B from its solution, it is more reactive than B. Figure reactions of metals with salt solution. Iron nail, cork, thread, test tube, iron nail, copper sulfate solution, test tube stand, copper wire, iron sulfate solution. Metal A plus salt solution of B tends to salt solution of A plus metal B. Which metal, copper or iron is more reactive according to your observations in activities? Comment this. The reactivity series. The reactivity series is a list of metals arranged in the order of their decreasing activities after performing displacement experiments activities, and the following series table known as the reactivity or activity series has been developed. Table: activity series, relative reactivities of metal. K potassium, Na sodium, Ca calcium, Mg magnesium, Al aluminium, Zn zinc, Fe iron, Pb lead, H hydrogen, Cu copper, Ag mercury, Ag silver, Au gold. Most reactivity decreases, least reactive. Questions? Do this and comment this. How do metals and non-metals react? In the above activities you saw the reactions of metals with a number of reagents. Why do metals react in this manner? Let us recall what we learned about the electronic configuration of elements in class 9. We learned the noble gases, which have a completely filled valence shell, show little chemical activity. We therefore explain the reactivity of element as a tendency to attain a completely filled valence shell. Let us have a look at the electronic configuration of noble gases and some metals and non-metals. We can see from table that a sodium atom has one electron in its outermost shell. If it loses the electron from its M shell, then its L shell now becomes the outermost shell, and that has a stable octet. The nucleus of this atom still has 11 protons, but the number of electrons has become 10. So there is a net positive charge giving us a sodium cation Na+. On the other hand, chlorine has 7 electrons in its outermost shell. Table: electronic configuration of some elements. Type of elements: element, atomic number, number of electrons in cells. Noble gases: helium He 22, a neon Ne 10 28, argon Ar 18 288, metal sodium Na 11 281, magnesium Mg 12 282, aluminum Al 13 283, potassium K 19 288 1, calcium Ca 20 2882. Non-metals: nitrogen N 725, oxygen O 826, fluorine F 927, phosphorus P 15 285, sulfur S 16 286, chlorine Cl 17 287. And it requires one more electron to complete its octet. If sodium and chlorine were to react, the electron lost by sodium could be taken up by chlorine. After gaining an electron, the chlorine atom gets a unit negative charge because its nucleus has 17 protons and there are 18 electrons in its K, L and M cells. This gives us a chloride anion C1-. So both these elements can have a give and take relation between them as follows figure. Na tends to Na plus E minus 281 28 sodium cation. Cl 287 plus E minus tends to Cl minus 288 chloride anion. Na plus Cl, Na plus Cl minus. Figure: formation of sodium chloride. Sodium and chloride ions, being oppositely charged, attract each other and are held by strong electrostatic force of attraction to exist as sodium chloride NaCl. It should be noted that sodium chloride does not exist as molecules but aggregates of oppositely charged ions. Let us see the formation of one more ionic compound, magnesium chloride. Figure. Mg 2 plus 2 minus 28228 magnesium cation Cl287 plus E minus tends to Cl minus 288 chloride anion Mg plus Cl tends to Mg2 plus Cl minus whole 2. Figure. Formation of magnesium chloride. The compounds formed in this manner by the transfer of electrons from a metal to a non-metal are known as ionic compounds or electrovalent compounds. Can you name the cation and anion present in MgCl2? Comment this. Properties of ionic compounds. To learn about the properties of ionic compounds, let us perform the following activity. Take samples of sodium chloride, potassium iodide, barium chloride, or any other salt from the science laboratory. What is the physical state of these salts? Take a small amount of a sample on a metal spatula and heat directly on the flame. Figure. Repeat with other samples. What did you observe? Did the samples impart any color to the flame? Do these compounds melt? Try to dissolve the samples in water, petrol, and kerosene. Are they soluble? Make a circuit as shown in figure and insert the electrodes into a solution of one salt. What did you observe? Test the other salt samples too in this manner. What is your inference about the nature of these compounds? Comment this. Figure. Heating a salt sample on a spatula containing sample burner. Figure. Testing the conductivity of a salt solution. Battery, bulb, switch, beaker, graphite rod, salt solution under test. Table. Melting and boiling points of some ionic compounds. Ionic compound. Melting point K, boiling point K. NaCl 1074 1686, LiCl 887 1600, CaCl2 1045 1900, CaO 2850 3120, MgCl2 981 1685. You may have observed the following general properties for ionic compounds. 1. Physical nature. Ionic compounds are solids and are somewhat hard because of the strong force of attraction between the positive and negative ions. These compounds are generally brittle and break into pieces when pressure is applied. 2. Melting and boiling points. Ionic compounds have high melting and boiling points suitable. This is because a considerable amount of energy is required to break the strong inter-ionic attraction. 3. Solubility. Electrovalent compounds are generally soluble in water and insoluble in solvents such as kerosene, petrol, etc. 4. Conduction of electricity. The conduction of electricity through a solution involves the movement of charged particles. A solution of ionic compounds in water contains ions which move to the opposite electrodes when electricity is passed through the solution. Ionic compounds in the solid state do not conduct electricity because movement of ions in the solid is not possible due to their rigid structure. But ionic compounds conduct electricity in the molten state. This is possible in the molten state since the electrostatic forces of attraction between the oppositely charged ions are overcome due to the heat. Thus, the ions move freely and conduct electricity. Questions? Do this and comment this. Occurrence of metals. The Earth's crust is the major source of metals. Seawater also contains some soluble salts such as sodium chloride, magnesium chloride, etc. The elements or compounds which occur naturally in the Earth's crust are known as minerals. At some places, minerals contain a very high percentage of particular metals and the metals can be profitably extracted from it. These minerals are called ores. Extraction of metals. You have learnt about the reactivity series of metals. Having this knowledge, you can easily understand how a metal is extracted from its ore. Some metals are found in the earth's crust in the free state. Some are found in the form of their compounds. The metals at the bottoms of the activity series are the least reactive. They are often found in a free state. For example, gold, silver, platinum, and copper are found in the free state. Copper and silver are also found in the combined state as their sulfide or oxide ores. The metals at the top of the activity series K, Na, Ca, Mg, and L are so reactive that they are never found in nature as free element. The metals in the middle of the activity series Zn, Fe, Pb, etc. the moderately reactive. They are found in the earth crust mainly as oxides, sulfides, or carbonates. You will find that the ores of many metals are oxides. This is because oxygen is a very reactive element and is very abundant on the earth. Thus, on the basis of reactivity, we can group the metals into the following three categories. 1. Metals of low reactivity. 2. Metals of medium reactivity. 3. Metals of high reactivity. Different techniques are to be used for obtaining the metals falling in each category. Several steps are involved in the extraction of pure metals from ores. A summary of these steps is given in figure. Each step is explained in detail in the following sections. Figure, activity series and related metallurgy. KNaCAMgAl electrolysis, ZnFePbCu reduction using carbon, AgAu found in native state. Figure, steps involved in the extraction of metals from ores. Ore, concentration of ore, metals of high reactivity, electrolysis of molten ore, pure metal, metals of medium reactivity, carbonate ore, calcination, oxide of metal, reduction to metal, purification metal, sulfide ore, roasting, metals of low reactivity, sulfide ores, roasting, metal, refining. Enrichment of ores. Ores mined from the earth are usually contaminated with large amounts of impurities such as soil, sand, etc. called gangue. The impurities must be removed from the ore prior to the extraction of the metal. The processes used for removing the gangue from the ore are based on the differences between the physical or chemical properties of the gangue and the ore. Different separation techniques are accordingly employed. Extracting metals low in the activity series. Metals low in the activity series are very unreactive. The oxides of these metals can be reduced to metals by heating alone. For example, cinnabar (HgS) is an ore of mercury. When it is heated in air, it is first converted into mercuric oxide (HgO). Mercuric oxide is then reduced to mercury on further heating. 2HgS solid plus 3O2 gas heat tends to 2HgO solid plus 2SO2 gas. 2HgO solid heat tends to 2Hg liquid plus O2 gas. Similarly, copper, which is found as Cu2S in nature, can be obtained from its ore by the just heating in air. 2 Cu2S plus 3O2 gas heat tends to 2 Cu2O solid plus 2SO2 gas. 2 Cu2O plus Cu2S heat tends to 6 Cu solid plus SO2 gas. Extracting metals in the middle of the activity series. The metals in the middle of the activity series, such as iron, zinc, lead, copper, are moderately reactive. These are usually present as sulfide or carbonates in nature. It is easier to obtain a metal from its oxide as compared to its sulfides and carbonates. Therefore, prior to reduction, the metal sulfides and carbonates must be converted into metal oxides. The sulfide ores are converted into oxides by heating strongly in the presence of excessive air. The process is known as roasting. The carbonate ores are changed into oxides by heating strongly in limited air. This process is known as calcination. The chemical reaction that takes place during roasting and calcination of zinc ores can be shown as follows. Roasting: 2 ZnS solid plus 3O2 gas heat tends to 2 ZnO solid plus 2SO2 gas. Calcination: ZnCO3 solid heat tends to ZnO solid plus CO2 gas. The metal oxides are then reduced to the corresponding metals by using suitable reducing agents such as carbon. For example, when zinc oxide is heated with carbon, it is reduced to metallic zinc. ZnO solid plus Cs tends to Zn solid plus Co gas. You are already familiar with the process of oxidation and reduction explained in the first chapter. Obtaining metals from their compounds is also a reduction process. Besides using carbon coke to reduce metal oxides to metals, sometimes displacement reactions can also be used. The highly reactive metals such as sodium, calcium, aluminium, etc. are used as reducing agents because they are displaced metals of lower reactivity from their compounds. For example, when manganese dioxide is heated with aluminium powder, the following reactions takes place. 3MnO2 S plus 4Al S tends to 3MnL plus 2Al2O3 S plus a heat. Can you identify the substances that are getting oxidized and reduced? These displacement reactions are highly exothermic. The amount of heat evolved is so large that the metals are produced in the molten state. In fact, the reaction of iron 3 oxides Fe2O3 with aluminium is used to join railway tracks or cracked machine parts. This reaction is known as the Thermit reaction. Fe2O3 solid plus 2Al solid tends to 2Fe liquid plus Al2O3 solid plus heat. Figure: thermit process for joining railway tracks. Extracting metals towards the top of the activity series. The metals high up in the reactivity series are very reactive. They cannot be obtained from their compounds by heating with carbon. For example, carbon cannot reduce the oxides of sodium, magnesium, calcium, aluminium, etc. to the respective metals. These metals are obtained by electrolytic reduction. For example, sodium, magnesium, and calcium are obtained by the electrolysis of their molten chlorides. The metals are deposited at the cathode, the negatively charged electrode, whereas chlorine is liberated at the anode, the positively charged electrode. The reactions are at cathode, Na plus E minus tends to Na. At anode, 2Cl minus tends to Cl2 plus 2E minus. Similarly, aluminium is obtained by the electrolytic reduction of aluminium oxide. Refining of metals. The metals produced by various reduction processes described above are not very pure. They contain impurities which must be removed to obtain pure metals. The most widely used methods for refining impure metals is electrolytic refining. Figure: electrolytic refining of copper. The electrolyte is a solution of acidified copper sulfate. The anode is impure copper, whereas the cathode is a stripe of pure copper. On passing electrical current, pure copper is deposited on the cathode. Key: cathode, anode, acidified copper sulfate solution, tank, impurities, anode mud. Electrolytic refining. Many metals such as copper, zinc, tin, nickel, silver, gold, etc. are refined electrolytically. In this process, the impure metals is made the anode and a thin strip of pure metals is made the cathode. A solution of the metal salt is used as an electrolyte. The apparatus is set up as shown in figure. On passing the current through the electrolyte, the pure metal from the anode dissolves into the electrolyte. An equivalent amount of pure metal from the electrolyte is deposited on the cathode. The soluble impurities go into the solution, whereas the insoluble impurities settle down at the bottom of the anode and are known as anode mud. Questions? Do this and comment this. Corrosion. You have learned the following about corrosion in chapter 1. Silver articles become black after some time when exposed to air. This is because it reacts with sulfur in the air to form a coating of silver sulfide. Copper reacts with moist carbon dioxide in the air and slowly loses its shiny brown surface and gains a green coat. This green substance is basic copper carbonate. Iron, when exposed to moist air for a long time, acquires a coating of a brown flaky substance called rust. Let us find out the condition under which iron rust. Activity: take 3 test tubes and place clear iron nails in each of them. Label these test tubes A, B and C. Pour some water in test tube A and cork it. Pour boiled distilled water in test tube B. Add about 1 milliliter of oil and cork it. The oil will float on water and prevent the air from dissolving in the water. Put some anhydrous calcium chloride in test tube C and cork it. Anhydrous calcium chloride will absorb the moisture, if any, from the air. Leave these test tubes for a few days and then observe. Figure investigating the conditions under which iron rust. In tube A, both air and water are present. In tube B, there is no air dissolved in the water. In tube C, the air is dry. A, B, C. Air, rusty iron nails. Water, air, layer of oil prevents air dissolving in the water. Boil distilled water, boil to remove any dissolved air. Dry air, anhydrous calcium chloride, drying agent. You will observe that iron nails rust in test tube A but they do not rust in test tube B and C. In the test tube A, the nails are exposed to both air and water. In the test tube B, the nails are exposed to only water. And the nails in test tube C are exposed to dry air. What does this tell us about the condition water which iron article rust? Prevention of corrosion. The rusting of iron can be prevented by painting, oiling, greasing, galvanizing, chrome plating, anodizing, or making alloys. Galvanization is a method of protecting steel and iron from rusting by coating them with a thin layer of zinc. The galvanized article is protected against rusting even if the zinc coating is broken. Can you reason this out? Annoying is a very good method of improving properties of a metal. When we can get the desired properties by this method, for example, iron is the most widely used metal, but it is never used in its pure state. This is because pure iron is very soft and stretches easily when hot, but if it is mixed with a small amount of carbon, about 0.05%, it becomes hard and strong. When iron is mixed with nickel and chromium, we get stainless steel, which is hard and does not rust. Thus, if iron is mixed with some other substance, its properties change. In fact, the properties of any metal can be changed if it is mixed with some other substances. The substance added may be a metal or a non-metal. An alloy is a homogeneous mixture of two or more metals, or a metal and a non-metal. It is prepared by first melting the primary metal and then dissolving the other elements in it in definite proportion. It is then cooled to room temperature. Do you know? Pure gold, known as 24 karat gold, is very soft. It is therefore not suitable for making jewelry. It is alloyed with either silver or copper to make it hard. Generally, in India, 22 karat gold is used for making ornament. It means that 22 parts of pure gold is alloyed with two parts of the either copper or silver. If one of the metals is mercury, then the alloy is known as an amalgam. The electrical conductivity and melting point of an alloy is less than that of pure metals. For example, brass, an alloy of copper and zinc, Cu and Zn, and bronze, an alloy of copper and tin, Cu and Sn, are not good conductor of electricity, whereas copper is used for making are not good conductors of electricity, whereas copper is used for making electrical circuits. So solder, an alloy of lead and tin, Pb and Sn, has a low melting point and is used for welding electrical wires together. Iron pillar at Delhi. The owner of ancient Indian metallurgy. The iron pillar near the Qutub Minar in Delhi was built more than 1600 years ago by the iron workers of India. They had developed a process which prevented from iron from rusting. For its quality of rust resistance, it has been examined by scientists from all parts of the world. The iron pillar is The iron pillar is 8 meter high and weight 6 tons, 6,000 kg. Questions? Do this and comment this. What we have learned: elements can be classified as metals and non-metals. Metals are lustrous, malleable, ductile, and are good conductors of heat and electricity. They are solid at room temperature, except mercury, which is liquid. Metals can form positive ions by losing electrons to non-metals. Metals combined with oxygen to form basic oxides. Aluminum oxides and zinc oxides show the properties of both basic as well as acidic oxides. These oxides are known as amphoteric oxides. Different metals have different reactivities with water and dilute acids. A list of common metals arranged in order of their decreasing Different metals have different reactivities with water and dilute acids. A list of common metals arranged in order of their decreasing reactivity is known as an activity series. Metals above hydrogen in the activity series can displace hydrogen from dilute acids. A more reactive metal displaces a less reactive metals from its salt solution. Metals occurs in nature as free elements or in the form of their compounds. The extraction of metals from their ores and then refining them for use is known as metallurgy. An alloy is a homogeneous mixture of two or more metals or a metal and a non-metal. The surface of some metals such as iron is corroded when they are exposed to moist air for a long period of time. The phenomenon is known as corrosion. Non-metals have properties opposites to that of metals. They are neither malleable nor ductile. They are bad conductors of heat. Non-metals have properties opposite to that of metals. They are neither malleable nor ductile. They are bad conductors of heat and electricity, except for graphite, which conducts electricity. Non-metals form negatively charged ion by gaining electrons when reacting with metals. Non-metals form oxides, which are either acids or normals. Non-metals do not displace hydrogen from dilute acids. They react with hydrogen to form hydride. Exercise: do this and comment this. Do this and comment this.